So this is the video I told you I was going to record to let you know more or less how we're going to do the presentation. So what we're doing is we're calculating the radius of the Earth using Erastothenes method. Remember, we're going to be doing this at 12:30 in your normal classroom. And this, by the way, is Erastothenes. Okay? So this is how we're going to do it. First of all, it's Alan's turn. There you go, Alan. This is what you have to do. So this is what Eratosthenes knew. In the 3rd century before the current era, Eratosthenes was the first to measure the radius of the Earth. This is what information he had. In Siena, current Aswan, when the sun is at its height, sunlight shines on the bottom of wells. At the same time, in Alexandria, the sun hits the obelisk, creating a shadow at an angle of 7.2 degrees. The distance from Siena to Alexandria is of 844.27 kilometers, about 5,000 stadia, in what used to be the way to measure distances. Here, let me show you a drawing, more or less of a diagram of what this looks like. Here, in point 1, you'd have Siena, current Aswan, and as you can see, the light is shining directly on it. It's a perfectly right angle. In Alexandria, however, the light is shining like this, following this yellow line, and therefore the obelisk here is creating a shadow. And now it will be Alexi's turn. So before we carry on, we need to learn a little bit of trigonometry, just to make sure that everybody here knows the trigonometry they need to know. It's not hard, don't worry about it. So this is more or less imagine the following situation. Here you have a circle. And in this circle, I know this angle here, and I know the radius. And the question would be, what is the length of the arc? What is the length of this red line? How do we calculate the length of this red line? So the first thing we're going to do is we're going to calculate the perimeter of the circle. And we know the perimeter of the circle, and this is a formula that I hope a lot of the parents can remember, is simply 2 times pi times r. Therefore, more or less, calculated, it should give you 25.13. That should be the length of the whole perimeter of the whole circle. Now, since the proportion of the angles must be the same, the proportion between the whole way around the circle, which is 360 degrees, the proportion between that 360 and 50.94 must be the same as the proportion between the length of this arc and the whole perimeter. I can therefore, since the proportions must be the same, calculate the arc length, that's the distance in red, using the Spanish trick, the regla de tres. This is how you do it. 360 degrees, that's for going all the way around, relates with 25.13. The same way that 50.94, which is this little part here, will relate directly with my arc length, with this distance. Now I can solve it. You do this times this, divided by this. And hence you get that the arc length is about 3.55. This is the principle of trigonometry that we need to be able to carry on. So let's actually reproduce Aristotle's calculation. And now it's Lara's turn. So Aristotle's calculation. Now the information Aristotle's had once more was that in Siena, the sun is at its height, the sunlight shines on the bottom of wells, that at the same time in Alexandria, the sun hits the obelisk, creating a shadow at an angle of 7.2 degrees, and he knew also the distance from Siena to Alexandria is of 844.27 kilometers. So, this is the situation. This is S stands for Siena. So we have the sun rays, and they're coming directly here, and they're hitting directly right on top of things in Siena. This is the obelisk in Alexandria. It's a lot taller in this diagram, but that's the obelisk in Alexandria, and it's casting a shadow. Now if we measure the angle at which it's casting the shadow, this angle here, that's 7 degrees. And if we think about it, this angle here must be the same as the angle at the center of the Earth between Alexandria and Siena. So you see, this looks a lot like the trigonometry we just did. Since the two angles are the same, and we know the length of the arc, that's 800 kilometers, and we know that, and we know the angle, we can reproduce the calculation. It's again a regla de tres. So 360 degrees, so we're going the whole way around, that would give me the whole perimeter of the Earth. And 7 degrees, 7.2 degrees, has to be related to 800, which is just this little angle here. Those, by the way, are the actual calculations. We just do the regla de tres, we solve. So 2 pi r is equal to this times this divided by this, and hence I get about 42,213.5. I divide that by 2 pi, and I estimate, and this was Erastothenes' calculation, that the radius of the Earth was about 6,718. By the way, the actual radius, now we know, is about 6,371. So it's pretty close. It's quite remarkable for the 3rd century before the Common Era. Now it will be Alan's turn. So what we will do today, we are going to reproduce the Erastothenes calculation. We will measure the angle of the shadow in our school at 1 o'clock. We'll use a computer program to calculate the angle in Oviedo at the same time. We will use another computer program to calculate the distance from Madrid to Oviedo. And once we have the distance from our school to Oviedo, we'll be able to calculate the angle. And once we have the angle, we'll do our own measurement with Erastothenes' method of the radius of the Earth. Just a quick note here, that the difference between the angles that we will measure, it will be equivalent to this angle here. This is a bit more of a complicated explanation that we will skip today, but you can ask the teacher and he'll be very delighted to explain it to you. And now Alan carries on, because Alan is going to open the programs and show how the measurements are done. So let's gather the data. And at this point, Alan, you show them you're going to calculate the angle from Madrid, and we're going to go to Stellarium, and you're going to get the data. Okay, and you're going to write it here. And then you're going to get the data from Oviedo, and you're going to write it here. And then you're going to go to Google Maps, and you're going to get the distance from Madrid to Oviedo. Just approximately this one. In the event that it crashes, I'll leave these numbers, so you don't have to change them. I can explain this to you on Saturday on the moment. Once the data is gathered, it will be Alexandra's turn. So let's make sure the data is in the right form. The computer program gave us the angle in degrees, minutes, and seconds. We have to change it just so that it's only in degrees with decimals to complement. So to do that, this is what you do. The angle from Madrid was 57 degrees, 53 minutes, 04 seconds. To change that into simply degrees, this is the calculation you have to do. 57 plus 53 divided by 60 plus 4 divided by 3,600. And that gives us 57.844 degrees. See, it's just a measurement in degrees with decimals to make up for the minutes and the seconds. We do the same thing for the angle from Oviedo. You get 54.72. And the distance, we don't have to change that. As we said, the angle from the center of the Earth to Madrid and Oviedo will be the difference between these two angles. And now for Lara to finish. Our final calculation with the data we gathered, we know that the angle between Oviedo and Secca Castillo is the difference between those two angles. That gives us 3.16 degrees. The length of the arc from Oviedo to Secca Castillo is 370.03 kilometers. So we can now reproduce the calculation. 360 degrees is all the way around the Earth, so that relates with the whole of the perimeter, which is 2 pi r. 3.16 degrees relates directly with my 370.03, which is the distance from Oviedo to Seca Castillo. 2 pi r is therefore equal to this times this divided by this. I calculate it, I get 42,155.3 divided by 2 pi, and my hour estimate in school today is 6,709.22 kilometers. Therefore, we're still quite far from the real radius, but we just use the same calculation as Erastothenes did. Thank you very much for your attention. That's the end of the presentation. Goodbye.